You know how the lighting in video games, even the really beautiful ones, still doesn't quite have that magic of a big blockbuster movie? Well, a lot of that comes down to just the sheer number of lights. Movies can spend hours, for a single frame, calculating millions of light sources. But trying to do that in real time, that has always been a huge, huge hurdle. Today, we're going to look at a breakthrough that completely changes the game.
Okay, so let's just get right into it. What you're looking at, this is the raw, unfiltered truth. This is what happens when a graphics card tries to calculate light from 3.4 times million sources for every single pixel on the screen, all in a tiny fraction of a second. It's just a blizzard of static. The computer is totally overwhelmed. It can only grab like one or two random samples of light for each pixel, and the result is this incoherent mess.
And that really brings us to the big question, right? How do we get from that blizzard of noise to a clear, photorealistic image and do it instantly? How do we solve a problem that needs a crazy amount of computational power, but do it inside the tiny time budget of a single frame?
This whole challenge, it actually has a name, the million light problem. And for people in real-time graphics, it's kind of one of the holy grails. You know, being able to render these massive, complex scenes with tons and tons of dynamic lights. Think of a huge city at night or a giant concert. Doing that interactively has just been computationally out of reach.
And the reason why, well, it's just simple math. For every single pixel on, say, a 1080p screen, and that's over 2 million pixels, you'd have to trace a line, a ray, all the way back to every single one of those 3.4 million lights to see if it contributes any light. I mean, we're talking about trillions of calculations per frame. It's just literally impossible to do in the 16 milliseconds you have if you want a smooth 60 frames per second. So you might be thinking, okay, why not just take that noisy image from the start and, clean it up with a filter? And that's a technique called denoising. It's definitely part of the solution, but it is not the whole story. The really crucial insight here is that you get way better results if you start with better data in the first place. Think about it like this. A denoiser is kind of like a really smart photo editor. If you give it a photo that's just a little bit blurry, it can sharpen it up and make it look great. But if you give it an image where huge details are just completely missing, where the important light information was never even captured, it can't magically invent that detail. It can smooth everything out, sure, but it can't bring back what was never there. And the researchers behind this whole ReSTIR algorithm, they said it perfectly in their paper. The key isn't just to have a better cleanup crew, it's to make less of a mess to begin with. The goal is to feed that final denoising step a much, much higher quality image right from the start, one that has already figured out the most important bits of lighting information. So how do you do that? How do you get better information without doing those trillions of calculations? Well, this is where the big aha moment comes in. The solution isn't about brute force. It's about a simple and, frankly, incredibly smart shortcut. Just think about that for a second. The old way of doing things treats every single pixel like it's on its own deserted island, forced to figure out this entire massive lighting problem all by itself. But what if we just changed that assumption? What if pixels could actually work together? And that is the core idea. Instead of one person trying to survey an entire city, what if you just asked your immediate neighbors and you all shared your results? I mean, if the pixel right next to me found a really bright, important light source, odds are pretty high that light is important for me too. By pooling all their knowledge, the pixels can work together to build a much more accurate picture of the scene's lighting for a tiny fraction of the work. Now, to make all this teamwork possible, the algorithm uses this really clever technique called reservoir sampling. What's so cool about it is how efficient it is. Imagine someone showed you 1 million different light samples, one right after another. Reservoir sampling lets you keep track of the single best, most important one you've seen so far without ever having to remember all million of them. It's like this tiny, super memory-efficient filter that's amazing at finding the needle in the haystack. And that brings us to the algorithm itself, ReSTIR. It uses this whole reservoir idea to create this amazing system of reusing information. And it's all built on two really powerful ideas. The first one is spatial reuse. That's our neighborhood watch program we were talking about. A pixel borrows the best light sample found by its neighbors right there on the screen. And the second one is temporal reuse. This one is even more powerful. A pixel can also borrow the best light sample it found in the previous frame of animation. It's actually using time as another source of information. So here's how it all comes together.
A pixel starts off, maybe it generates one or two of its own random light samples. Then it looks at what its neighbors found, and it merges their best sample into its own pool. Then it looks back in time to the last frame and merges that best sample too. All of a sudden, that one pixel has effectively picked the best option from a huge pool of high-quality, pre-filtered candidates. It ends up with an incredibly smart guess about what the light should look like.
Okay, so that's the theory. Teamwork between pixels across space and time. But what does it actually look like when you put it into practice? Well, the result is, it's nothing short of a revolution for real-time graphics. And I mean, the results, they really speak for themselves. On the left, you're seeing an image made with an older but still state-of-the-art technique. It's noisy, a lot of details get lost. On the right, using the exact same amount of render time, is the result from ReSTIR. The image is clean, the shadows are sharp, all the detail is there. It's just a night and day difference.
So just how big of a difference are we talking about? Well, the research paper found that to get the same final image quality, the ReSTIR algorithm can be anywhere from 35 to 65 times faster than the previous methods. This isn't just, a small improvement. It's a massive generational leap.
What's neat is the algorithm even comes in two flavors. You've got an unbiased mode, which is mathematically perfect and guarantees no light energy is lost. And then there's a biased mode, which is even faster and cuts down noise even more, but it has a tiny risk of some minor darkening in really complex scenes. It's this flexible tool that lets developers choose what they care about most, perfect accuracy or maximum speed.
This is really cool, because this slide basically lets us watch the algorithm thinking in real time. It shows how adding more rounds of that spatial reuse, letting the pixels talk to their neighbors more and more, just progressively cleans up the image. So we start with that initial noisy mess. After just one round of reuse, it's already way better. By the time we get to 4 iterations, the image just snaps into focus. And this all happens in just a few extra milliseconds. So a 65x speedup is incredible, but what does it actually mean for us? Because this isn't just some academic paper. This technology is unlocking a future for interactive experiences that, honestly, used to be just a dream.
The impact is going to be huge. For video games, this means worlds that are way denser, more dynamic, with far more realistic lighting. For filmmakers who use virtual sets, it means they can see movie-quality lighting live, right there on set. Architects can walk their clients through these stunningly realistic virtual buildings in an instant. And digital artists, they're finally freed from that tyranny of waiting for the render bar, able to just create at the speed of thought.
When you boil it all down, the most important thing is this. ReSTIR is fundamentally blurring the line between the pre-rendered world of movie CGI and the interactive world of real-time graphics. The kind of lighting complexity that used to take a whole render farm hours to create is now possible instantly on a regular desktop computer.
And that leaves us with a pretty thrilling question. For decades, the digital worlds we could build were limited by how expensive it was to calculate light. Now that barrier is being shattered and rendering millions of lights is becoming almost trivial, what kind of impossible, beautiful, and breathtakingly complex worlds are we going to imagine and build next?